Welcome to this lecture. This is the last lecture of week 7. In this week, we have looked at limiting behavior of measure theoretic integration and also explored the connection between Riemann integration and Lebesgue integration. So in particular, the applications of these limit theorems involving integrations and the proof of the connection between Riemann and Lebesgue integrations were incomplete. So we will discuss this in this lecture. So let us move ahead to the slides and start the discussion. Okay. So in the previous lecture we started this discussion on the connection between Riemann and Lebesgue integration, and there the main theorem was theorem 5, which said that existence of Riemann integration will imply the existence of Lebesgue integration. So we said that we will do it in this lecture. So let's start with that. So start with assuming that you have a function defined on this closed bounded interval AB, a bounded function such that it's Riemann integrable. In that case, what do? You look at this sequence of partitions. Let's denote them by script P subscript K, such that this sequence of partitions has this property that the mesh size or the length of the largest subinterval that goes to 0 as k goes to infinity. So you are taking finer and finer partitions of the domain set closed A to closed B. Okay, and you can also, without loss of generality, assume that Pk plus 1 is a refinement of Pk. Okay, so this is true for all k. So you can assume that. Right. So under this setup, provided that you have the existence of this Riemann integration, what do? You look at the limit of the upper Riemann sum and lower Riemann sum. So how are they defined? So for any partition script P, you look at these expressions where you have these capital Mj denoting the supremum value of the function within an interval Tj minus 1 to Tj, and small mj denotes the infimum of the function within this interval Tj minus 1 to Tj. So provided you have these two quantities, capital Mj and small mj, what do? You just approximate the area under the curve from above by this upper sum and from the below by this lower Riemann sums, right? So for any partition P where the points are made up of this T0, T1 up to Tn, these many points, you can rewrite it in this formulation, right? So these are the upper Riemann sum and the lower Riemann sum, and provided the Riemann integration exists, so for this sequence of partitions that you have chosen, you must have that the limit of upper Riemann sum will be equal to the limit of lower Riemann sums, and that should equal this value, which is the definition of Riemann integration. Alright, fine. Now we would like to make the connection with Lebesgue integration. So far what we have discussed are recalling facts about Riemann integration. Alright, so let's move ahead. So now for any such partition P, you can consider a simple function defined on this closed bounded interval AB. So what is this? So look at f super bar script P. Okay, so what is this? I look at these kind of indicators of left open right closed interval Tj minus 1 to Tj. So look at that indicator and multiply by the supremum value of the function within that interval. Okay, and look at the summation. Similarly, f lower bar superscript P, you would look at in terms of this combination of these indicators of the intervals, multiplying it by this infimum of the function within the interval. Okay, alright. So now observe that if you were to look at these simple functions, here if you integrate the f super bar function with respect to the Lebesgue measure, you will get back mj multiplied by the length of the interval Tj minus 1 to Tj, and that is nothing but mj multiplied by Tj minus 1. So that summation, right? So therefore you are just getting back the upper Riemann sum for that specific partition. Similarly, if you are going to look at this f lower bar, that function, then if you integrate it against the Lebesgue measure, you are again going to get back that summation mj times tj minus 1, right? So that is going to give you back the lower Riemann sum. Now with this observation, what you can now claim is that you have some connection with the upper Riemann sum and lower Riemann sum and certain kind of integrations involving these kind of simple functions that you have chosen based on the partitions, right? Alright, but let's explore these f superbar and f lower bar functions a bit more. So for that given sequence of partitions script pk, look at f superbar and f lower bar. Okay, so consider this, but f is given to be bounded, so therefore these functions by definition f lower bar and f upper bar, these functions are bounded by that same constant that bounds the actual function f, right? So these are bounded simple functions defined on this closed bounded interval ab. Alright, now it can also be checked very easily that f superbar pk is non-increasing in k and f lower bar pk is non-decreasing in k. Okay, so you can easily check this. Now once you have this fact, you will immediately look at the limit function. So once you have some kind of a monotonicity behavior, you can look at the pointwise limits in k. Okay, so for every fixed point in the domain, you let k go to infinity, get that limit value. That will give you these functions f upper bar and f lower bar. Okay, so for that specific choice of the partitions that you have started off with, look at these limit functions f upper bar and f lower bar. But observe that these functions are limit of measurable functions. In particular, these functions are limit of simple functions, right? So therefore this f upper bar and f lower bar must be Borel measurable. Okay, all right, but now recall that Lebesgue measure, if you are restricting your attention to this closed bound interval ab, that's a finite measure. And then we had discussed earlier in note 13 that there is a version for bounded convergence theorem for finite measures. Okay, so as long as you have the functions, the sequence of functions are uniformly bounded and you are dealing with integrations with respect to a finite measure, you can talk about the bounded convergence theorems. So in particular here, look at the integration of f upper bar over this interval closed ab. Now this by the bounded convergence theorem will be exactly the limit of the integrations of the approximating sequence of functions. So that is f upper bar pk. So pointwise it converges to this, so you can exchange the order of limits and integrations. But observe that f upper bar pk integration with respect to the Lebesgue measure, that we have identified as the upper Riemann sum for the partition pk, right? So therefore you have this equality now. But this as per definition agrees with the actual Riemann integration of the given function f, right? So this is the integration with respect to the Riemann sense. Alright, but then that also agrees with the limit of the lower Riemann sums, but then lower Riemann sums you can identify it as the integration of f lower bar pk with respect to the Lebesgue measure lambda. Okay, but then again you push the limit inside, again you apply the bounded convergence theorem, you end up with the fact that this is the integration of f lower bar with respect to the Lebesgue measure. Okay, so now all these expressions are equal, but observe the leftmost term that is involving the f upper bar function and the rightmost term that is involving the f lower bar function. By definition f upper bar is greater or equals to f lower bar, you have that. So this is by construction, and you also have that these functions have these nice integrations and they are equal, right? So you can immediately claim that the difference function f upper bar minus f lower bar, if you look at that function, that's a non-negative function and that integration with respect to the Lebesgue measure is 0. Now you have this non-negative function whose integration is 0, and by an earlier proposition you will immediately claim that these two functions must match almost everywhere. Okay, so that's good. So we have now made some identification about these two functions, f upper bar and f lower bar. But observe that when this equality holds, at the points whenever this equality holds, you have by definition that f upper bar is equal to the actual function value at x, and that will agree with the f lower bar function evaluated at x. Okay, so all these three functions will agree once you have the equality between the f upper bar and f lower bar. So why is this? This is following the fact that by definition the function value, the actual function value f, falls between f upper bar and f lower bar. Okay, so this is easy fact to check. This is by definition of the functions f upper bar and f lower bar. Okay, so once you have that, you claimed that f upper bar and f lower bar agree almost everywhere, so therefore you have actually this equality. So remember, if you have so far not shown anything about the measurable structure of the function f, it's just taken to be bounded function defined on the closed and bounded interval ab, but you are now saying that it is matching with these measurable functions almost everywhere, right? So you have these functions f upper bar and f lower bar. These are all nice Borel measurable functions which turned out to be limits of certain simple functions. Now the given function f is agreeing with a Borel measurable function Lebesgue measure almost everywhere. Provided this happens, it can now be shown that f is actually measurable with respect to the Lebesgue sigma field. So remember, we had discussed this Lebesgue sigma field in note 8 earlier. So what we had mentioned was that the Borel sigma field with respect to the Lebesgue measure is not complete, meaning it does not contain all subsets of measure 0 sets. If you include all those subsets of measure 0 sets and generate a further sigma field, you will get the Lebesgue sigma field. Okay, so that's a enlarged sigma field, and with respect to that you can now claim that if a arbitrary function matches with a Borel measurable function almost everywhere, you can actually claim that if the given function must be measurable with respect to this bigger sigma field. So it's not necessarily measurable with respect to the Borel sigma field, but it is measurable with respect to the Lebesgue sigma field. So this is an important clarification that was required if you want to consider the integration of the function f with respect to the Lebesgue measure. Okay, so remember, you can only talk about integrations of measurable functions, so that's why this clarification was necessary. But just to avoid all these technical details associated to completion of sigma fields and regarding this connection with almost everywhere identifications with measurable functions, we avoid the details. We want to avoid that, and we are just saying that this fact is true. We will just take this as true and we will continue the discussion. Okay, now the upshot is this, that you have so far shown that if that general function that you have taken, if it is Riemann integrable, then it turns out to be measurable with respect to an appropriate sigma field, okay, which is the Lebesgue sigma field. Alright, but then you can now consider the integration of the function f with respect to the Lebesgue measure. You have a measurable function, you can consider this. But then by the identification of the equalities that you have observed, you can now claim that since f agrees with f upper bar and f lower bar almost everywhere, then their integrations will also match if you consider the integration with respect to the Lebesgue measure. So the last equality here is true because two functions f and f lower bar both are now measurable and both agree almost everywhere, so therefore their integrals will match. So here you are using the fact that the Borel measurable functions f upper bar and f lower bar are also measurable with respect to the Lebesgue sigma field. This is easy to check because as long as all the pre-images are in the Borel sigma field, it is also in the enlarged sigma field, which is the Lebesgue sigma field. Okay, so measurability of f upper bar and f lower bar is not an issue. Alright, so you have this equality, but you have earlier shown that the integration of f upper bar and f lower bar that agrees with the actual Riemann integration of the given function f. So that is the equality that are listed right here in front, right? So let's just go back. So you had earlier proved this equality, right? So you had just look at this part here. This part immediately tells you that integration of f upper bar and f lower bar match, and that agrees with the actual Riemann integration of the given function f. Alright. So with that, what you have managed to show is that f is now integrable in the Lebesgue sense. So you are now considering Lebesgue integration of the function f, and that is matching with the Riemann integration of the given function f. Alright. So this was the statement of the first part. Okay. So this was the first statement in the theorem 5. Now the second half gave a characterization of Riemann integration, right? So for completeness, we are just going to discuss this proof very briefly. Okay. So again, all these verifications can be done explicitly, but let's focus on the main parts here. So again, go back to these partitions pk. Okay. So this is the shrinking sequence of partitions. By shrinking, I mean the mesh size decreases and decreases to 0. Okay. So now look at these endpoints of all the subintervals that are listed under these partitions. Okay. So if you consider any fixed partition, it has a finite number of intervals listed, and each subinterval there will have two endpoints. If you look at all the endpoints of all the subintervals in all the partitions, then you end up with a countable set. Okay. Now here note that on this countable set, the Lebesgue measure associates zero mass. Okay. So you don't want to care about these endpoints, and you don't want to care about the function values at these endpoints. So while considering integrations, we don't want to care about the function values on these endpoints. So ignore this set of measure 0 first. Now, while determining this set of discontinuities of this function, which is the effectively the statement that characterizes the Riemann integration, as we are trying to show, we are going to ignore the endpoints because that anyway is a set of measure 0. So now we ignore that set and we focus purely on the interior points of all these subintervals, and we want to check whether certain discontinuities are occurring there or not. Now for all the other points inside the interval closed AB, you have this inequality. Again, this is by definition that f upper bar is greater or equals to given function f is greater or equals to f lower bar. Alright. But now remember that almost everywhere this equality holds, right? So f upper bar, f and f lower bar matches lambda almost everywhere, meaning outside some appropriate null set the function values match. Now you can show that if this happens, then f is actually continuous at that point. Okay. Now that immediately tells you that on these points where these function values match, you immediately will claim that f is continuous, and therefore the set of discontinuity points will have measure 0. Okay. So you have to throw out all these points where the discontinuities are not occurring. So these are all the points where f is continuous. So only possible discontinuities occur when f upper bar is not equal to f lower bar. That's when possible discontinuities of the given function f might occur. Okay. So this is a statement that we will take it as a fact. Alright. So therefore the proof now follows that you have started off with this Riemann integration structure, and then you have identified the Riemann integration with the Lebesgue integration, and you have also identified the characterization of Riemann integration functions as in terms of the set of points of discontinuities. Okay. Alright. Now we are going to focus on applications of this result. So we are now using the fact that we have discussed these limiting behaviors of integrable functions, and we have also discussed these connections between Riemann and Lebesgue integration. Alright. So now let us focus on the applications of this, and we will look at an explicit example of limit of integrations. Look at these functions n times sin x by n divided by x times 1 plus x squared. So look at these functions on the interval 0 to infinity. Look at their integration and look at the limit as n goes to infinity. Call that limit as capital A. We want to compute this limit capital A. Now what do you do? First, this is a given Riemann integration for each fixed n. You want to first go to the Lebesgue integration, and that's where you are going to apply the appropriate dominated convergence theorem. So let us look at this identification in terms of the Lebesgue integration. So choose a sequence Fn of non-negative measurable functions given by this. So we are looking at functions on this interval open 0 to infinity. So here what is happening is that you ignore the value at 0. Okay, so that's fine, because Lebesgue measure anyway associates 0 mass to singletons. So therefore you ignore the function value there. So you are just multiplying by this indicator to get rid of all these other values. Okay, alright. So now look at the actual function, which is given function n times sine of x by n divided by x times 1 plus x square. Look at this. Now you want to compute that limit a, right? So now this Riemann integration is nothing but the integration of the function Fn with respect to the Lebesgue measure, right? So therefore you simply write that a equals limit of integrations of Fn with respect to the Lebesgue measure. Now you want to apply the dct, but before that you would like to first compute the pointwise limit of this functions Fn. Now you are focusing your attention only on the positive part of the real line, right? Because anyway on the other parts the function value is 0, so that will not contribute to this integration. So let's look at x to be positive. In this case, look at this expression and let n go to infinity. So this is the pointwise limit. So bring out 1 by 1 plus x square, that does not depend on n anyway. Now write the remaining part as sine x by n divided by x by n. Now for any fixed x, x over n goes to 0. So therefore you have this standard limit which goes to 1. So therefore you end up with this limit function which is 1 by 1 plus x square. So therefore the limit functions of these functions Fn is exactly 1 by 1 plus x square on the interval 0 to infinity. Otherwise the limit function is 0. Now our idea is to obtain a uniform bound of these functions in terms of a integrable function. In preparation for that, let us first consider this function g defined on this interval close 0 to open infinity and taking values in the set of real numbers. So how is this defined? So for positive y, look at the ratio sine y by y. At the point y equal to 0, assign the value 1. What you can now easily check is that this function is bounded and continuous. Okay, so please take this as an exercise. This function will be used to obtain the bound for the functions Fn. Now let C be a positive quantity such that this function g is bounded by that constant c. Okay, so you have proved that this g function as defined above is bounded and continuous. So therefore you will get some positive real number which will bound this. Now look at the bound of Fn given by these constants. So how? So look at this modulus quantity. So that is again in the form of the function g, right? Now g is uniformly bounded by this constant c, so therefore you get the bound c times 1 by 1 plus x square multiplied by the indicator, right? Now to apply the dominated convergence theorem, you need the integrability of the bound function, right? So this is the upper bound function and you need the integrability of that. So just try to integrate this. I am ignoring the constant here, it doesn't matter because c is some positive constant. Alright, good. So now this one is nothing but the usual Riemann integration from 0 to infinity dx by 1 plus x squared, right? So this is the usual Riemann integration. Now here you can use the standard trigonometric transformation that x equals to tan theta and compute this. There are other methods of computing this, but this is one of the methods and that will give you some finite value. So therefore this non-negative function is integrable, and therefore you are now allowed to apply dct to push the limit inside in this computation. So limit value, that is a, can be computed at integration of the limit functions, right? But then you have computed the limit function as 1 by 1 plus x squared multiplied by the indicator. So therefore again you go back to the usual Riemann integration, and that will be just integration 0 to infinity of dx by 1 plus x squared, which you have already computed. That will be some finite quantity anyway. Okay, so this is an application of the dct as well as the connection between Riemann and Lebesgue integration. So you have seen that in many of the steps we have moved back and forth between Riemann and Lebesgue integrations. Alright. So as soon as you can compute this final integration in the Riemann sense, you will get back the value of the limit. But in between we had applied these measure theoretic arguments to apply the DCT. Okay, that allowed us to push the limit inside. Alright. So now we have seen these applications of these limit theorems. But there are some few comments about certain more general notions of integrations. So the first comment here is about Riemann-Stieltjes integrations with respect to distribution functions. So if you take a distribution function, so that is a function defined on the real line taking values between 0 and 1, and its non-decreasing right continuous, limit at infinity is 1, limit at minus infinity is 0. To take such a function capital F. Now take another function small f which is defined on the interval closed AB taking real values. Okay, and then consider this limit for any partition like this. So choose a partition of the closed bound interval AB and look at this quantity. So this is the usual Riemann sum, except that in a Riemann sum you will look at this Ti plus 1 minus Ti, but here you are looking at the increment of the distribution function. So instead of looking at this Ti plus 1 minus Ti, you are looking at the increment of the distribution function. That's the only difference which you are considering here. So with some appropriate hypothesis, you can establish the existence of the limit for appropriate functions f and small f. Okay. So now here what is happening is that once you get this limit, this is what is known as the Riemann-Stieltjes integration. So we are not going into the exact definition of the Riemann-Stieltjes integration, we are just indicating the idea. Now once you have this integration from small a to small b, you can also possibly consider integrations over the whole real line, and this will be similar in definition, okay, as considered for the Riemann integration case. So you can consider integrations of functions f with respect to distribution functions. Okay, all right. Now there is a general version of this which is called the Lebesgue-Stieltjes integration. So again you start with a distribution function, but now you start with a measurable function as the integrand, and then given this function capital F, you get a probability measure mu subscript f defined on the this measurable space real line together with the Borel sigma field. Now try to integrate this measurable function with respect to this probability measure. If you can define it, then you call it the Lebesgue-Stieltjes integration of small f with respect to the distribution function capital F. Okay, so this is the notation that we are introducing. This is nothing but the integration of the small f with respect to the corresponding probability measure. Okay, now once you have considered this minus infinity to plus infinity integration, that integration you can also consider integrations over intervals like closed AB. Okay, so that will run similar to the earlier discussions. Okay, here once you have this measure theoretic structures, it is just defined as integration of f of x multiplied by this indicator function here. Okay, so that is just cutting off the function values outside this interval. Okay, so outside this interval this product is 0, so that does not contribute to the integral. So that is basically the idea behind this definition. So this is what we had also considered in Lebesgue integrations or measure theoretic integrations. Alright, now we have this identification between Riemann integrations and Lebesgue integrations. So that was discussed in theorem 5. But you can also get an identification between Riemann-Stieltjes integration and Lebesgue-Stieltjes integrations. So you can state this in a similar fashion and prove it with appropriate justifications. So we are not going into the details. Alright, but here is something which is quite interesting since we are interested in expectations of random variables. So you can identify the expectation of random variables as some kind of a Lebesgue-Stieltjes integration. So how do you do this? So look at a random variable defined on some probability space omega fp. Then its law is p compose x inverse, and you can also consider the corresponding distribution function f subscript capital X. Then for any measurable function, you can now consider expected value of g of x, and that is by an appropriate change of measure argument can be written as integration of the function g with respect to the law p compose x inverse. So this we had discussed earlier. But now, as per the discussion in this lecture, P compose X inverse is exactly the probability measure corresponding to the distribution function, right? And therefore, you will immediately write it as a Lebesgue-Stieltjes integration of the function small g with respect to the distribution function. So this last integration is being interpreted as a Lebesgue-Stieltjes integration, okay? And that will exist provided you can make sense of this integration with respect to this appropriate probability measure P compose X inverse. So you can write down expectations as some kind of a Lebesgue-Stieltjes integration with respect to distribution functions. Alright. Now an important function in these discussions about random variables is called the characteristic function. So now that we have discussed about integrations with respect to measures, you can now come back to this specific type of a function. So what do? Again, continue with a random variable x and consider this function denoted as phi subscript capital X. Okay, so that is a function defined on the real line and takes values in the set of complex numbers. So this is defined as follows. So for any fixed u in the real line, you look at expected value of exponential I u x. Okay, and that is by definition the integration of the function exponential I u x omega with respect to the probability measure. Okay, but now what does this function look like? So split it into real part and imaginary part. So here this is nothing but in terms of cosines and sines. Okay, so this is a familiar formula to you. Now once you look at this formula, these are now integrations of nice measurable functions with respect to a probability measure, right? So that's what we are looking at here. Okay, so these are now nice random variables. These compositions are nice random variables and you are integrating it with respect to the probability measure. So therefore these things are well defined. So integrations existence is fine, but then you change variables and you go to integration with respect to P compose X inverse. Once you do that, you get back this familiar formula that this is integration of exponential I u small x with respect to the log. Okay, alright. So you will see more calculations involving this in later, but what you can now try to do is that you can take discrete random variables and try to compute these characteristic functions, and this will match with whatever you have earlier seen in your basic probability course. And an important comment here is this, that these random variables cos u capital X and sin u capital X, which we had used in these integrations, they are actually bounded random variables, right? So for any fixed u, these are bounded random variables and therefore they are integrable with respect to the probability measure. And hence for any fixed small u, this quantity is well defined. So this always exists. By definition, this is taking values in the set of complex numbers. Alright. So this is called the characteristic function of the random variable capital X. And as discussed earlier, as we have just mentioned, that for the case of discrete random variables, you can write down expressions or computations of these characteristic functions. Alright. So the computations will run similar to whatever we have discussed earlier in week 6. Alright. Now the case for absolutely continuous random variables will be discussed in the next week, but it is a fact that given this characteristic function, you can recover the law of the random variable. Okay, this is a very important fact. Another way to state this is that the characteristic function uniquely determines the law or distribution of the random variable x. So this is a very important statement. Alright. Now another point to note is that we have defined this characteristic function as taking values in the set of complex numbers. You can actually consider the measurable structure with respect to the complex numbers together with the Borel sigma field by appropriately defining the Borel sigma field on the set of complex numbers. But we are not going into the details here. We take the easier route. We go via the real part and imaginary part and make sense of their integrations. Okay. Alright. So a final comment as we stop is that if you are talking about these random variables with a specified law, we are going to use this notation x follows mu, meaning x has this law mu or x tilde mu. So this symbol refers to the fact that x is a random variable with this law mu. This notation shall be used extensively in our discussion next week. So there we will put everything together that we have learned in this course so far, and we will also discuss about the absolutely continuous random variables. Alright, so that discussion we will do in the next week's discussion. We stop here.